welcome back to our next lecture on operating system. This is Unit 2's last part, which is process synchronization. Let's see what we are going to cover in this section. We will first see the background of process synchronization. What is process synchronization? Then we'll understand what is the critical section problem. Then we'll understand Peterson's solutions for critical sections. And then we will understand some of the hardware solutions for solving the process synchronization problem. Then we have Newton's law. Then we have semaphores. Then next we will be studying some of the classical problems of synchronization. And last we will be seeing what are monitors. So this is what we will be studying in under the chapter of process synchronization. So let's start with the background. So let's understand what is this process synchronization and why we need process synchronization. First of all, in an operating system, processes will be working in a RAM. There will be more than one processes, and these processes may be cooperating processes. Now, what do you mean by cooperative processes? Cooperative processes means that two or more processes may be working together on some data. They may be using shared data. So that is what is cooperative processing. They need to work simultaneously, concurrently, and they need to work on, they will be sharing some data. So examples of such systems or such applications are when you have a process with multiple threads. So we have understood threads in our last chapter or in our last video, and we know that in one process only multiple tasks can be allocated to independent threads and they can be executed by these threads. So this kind of a scenario is one such example of cooperative processes. Another one is when two different processes are working on some shared memory. They are accessing some shared memory. This shared memory can be a file or it can be a message passing technique that is used between two processes to share the data. So these are some examples of cooperative processes. Now, in cooperative processes, there is a situation that can occur that there can be inconsistent data. Now, how this inconsistency of data happens? When there are two processes working, so maybe two processes will simultaneously manipulate the data, because of which the data can become inconsistent. This example, the best example for this is the producer-consumer problem. Supposing the producer is producing some items and consumer is consuming simultaneously. So the amount of products that are available in the market can be a little confusing one, because producer also is manipulating the amount, quantity that is available in the market, and the consumer is also manipulating the value of the quantity of the products available in the market, because of which there can be data inconsistency. We'll see this example in detail, how this data inconsistency happens. So what we see here is that concurrent access to shared data may result in data consistency. So we will come across a lot of examples where we will be having such scenarios where we are accessing shared data and how we are securing the shared data access for two processes or two or more processes simultaneously. What we need to do here is, if we don't want the data to be inconsistent, we need to take care that the two processes that are accessing the shared data should not manipulate the data simultaneously. If one process is already manipulating such a shared data, we need to restrict the other process from accessing such a shared data. It is simple. What will happen if there is a class of students and two faculties enter to explain? So it's a difficult task for the students to understand what to learn. So one class, there is one faculty to teach. So that is what we are going to do. At one time, only one process can manipulate the data, not two processes manipulating the same data. So we need to restrict it. So there are some techniques, as we saw in the beginning, Peterson's solution, then we had mutex, then we had semaphores. All these are the ways of doing this. So we will study all of these one by one. So let's understand what next. Maintaining data consistency requires mechanisms to ensure orderly execution of the cooperating processes. That is what I have told you, that if there is a class of few students sitting, then two faculties cannot enter the classroom and start explaining the concept. Only one person at a time can enter and teach the class. So that is what we are achieving here. So we need to have some mechanism to ensure that only one process accesses the shared data. Not two processes should not access such shared data. Example, I told you the producer-consumer problem. So here, supposing that the producer has produced 10 products and in the market there are already 5 products available. So products available in market are 5. Producer has produced new 10 products. So total amount of products in the market are 15. Now if consumer consumes 3 products, initially products available in the market are 5. Consumer at the same time, when producer is adding new products, consumer is simultaneously consuming the item. So he consumes, out of the 5 available, he consumes 3 products. So how many are remaining? 2. What is the correct value of the number of products available in the market? It is neither 15 nor it is 2. Actually, it was 15 minus 3, 12. The answer should be 12. 12 is the correct products available because 2 were consumed, 10 were produced, total was 12. So actual products, number of products in the market should be 12, but because each of the consumer process as well as the producer process has taken the value 5 and they have manipulated, the producer has added 10 products and consumer has consumed 3 products, we are getting wrong data. So this is inconsistent data and this is the right data. So how can we get this right data? What we should do is, when is adding the products to the product shelf, the consumer should be restricted. The consumer should be restricted. Or if the consumer is consuming the product, then the producer should be restricted from adding the products to the shelf. Right? Is it right? So that is how you will get a consistent amount of products that are available in the market. So that is how we will be trying to fix. We need to fix this problem. So let's say this example as a code. Here, while true means while always. The producer is always producing, the consumer is always consuming. So it is an infinite process. So we are taking it while true, the first statement. Next we say that there is a comment which says produce an item in the next produce. So the producer is going to produce a new item. So while counter is not equal to buffer size. Now what is this buffer size? Buffer size is your shelf size. If your shelf is full, then you cannot add new products to the shelf. So you need to wait for the consumer to consume some product so that the shelf there is some space for you to add new products. So you need to wait for the buffer size to be less than the number of items, that is the counter should be less than the buffer size. If it is less than the buffer size, it means that there is space on the shelf to add new products. So we will have to wait for the counter to be less than the buffer size. So if counter is equal to buffer size, can you see there is a semicolon there which says that the while loop should repeat constantly so that the producer waits for the shelf to become empty or some part of it to be empty. When the counter is less than the buffer, the while condition becomes false and it comes to the statement where it says the buffer in is equal to next produce. So the buffer is the shelf, you can say that it is the shelf, and in that shelf, this particular location is empty, it's free. So you can add your new products to that shelf. Next, in is equal to in plus 1 more buffer size. You need to see increment the in means the buffer empty position is counter. So where is it empty? Next position that is empty. We are checking that. So we are saying n is equal to n plus 1 mod buffer. It is same like your circular queue. So if you see your circular queue, circular queue, this is buffer, this is called buffer. So in is from where the producer is entering the product, he is adding the product to the buffer, and out is a counter that is used by the consumer to consume the product. So out is your rear of your queue and in is the front of your queue. So producer will be adding products to the buffer, to this buffer, which is a circular queue, and hence we are taking in is equal to in plus 1. So if this is 0 and this is, for example, 8 or 5, then we say in is 0. So next in is equal to 0 plus 1 mod buffer size. So whatever is the number of elements, how many elements can it store? So this is 0, 1, 2, 3, 4, 5, 6, 7, 8. So that case it should be 6. So totally how many buffer size is what? 9. So now in is equals to 0 plus 1 mod 9, which is equals to 1. So in will get incremented to this place. So the next product that will be produced by the producer will be added to the location 1. Similarly, it will go on to the next and it will again come back to 0. So till then, the consumer will consume the products that are there and it will come back here. So as the consumer goes on consuming the item, these positions will go on becoming empty for the producer to add the elements. So that is what is this code doing here. So we say counter plus plus. So now just now we added one product to this place, it has become the counter increment. So if there are the counter value now, counter 1, 2, 3, 4. So counter is equal to 4 and in is pointing at 1. So if producer again produces, it checks whether the counter is equal to buffer size. Counter is 4, buffer size is 9. Because the counter is not equal to buffer size, the next product produced can be added to the buffer in. So then we can add a product, the next product in 1 and again incremented and in becomes 2 now. So in has come from 0 to 2 now. Then again it will add and again this will become full, this will become full, this will become full, this will become full, and every time it is getting counter value is increasing. So now counter becomes 9. The counter is equal to buffer size, so the producer has to wait for the consumer to consume the item. So this is what we are doing here. Next, let's see the consumer's code. The consumer code is same. So again we are saying, well, counter is equal to 0. Why we have to check for the counter is equals to 0? Counter equal to 0 means that there are no products added to this queue or to this buffer and hence counter is 0. But right now counter is 9. It means that as many shelves can hold, how many items shelf can hold, all those items are saved or put on the shelf and consumer can pick any of these items. So it will pick the item that is pointed by the out counter. So here you see, while counter is equal to 0, counter is right now 9, it's not 0. So next consumed is equal to buffer out. So from the buffer array, whatever is the out position, that element is removed. So this becomes empty now. The consumer has consumed this product and hence there is a empty space in our shelf. Next, we have counter minus minus. So counter was 9, counter will now become 8. Right? Next, again if you see, if we repeat this process, the out has got incremented. I have left that point in between. So now count has, in the previous example, as I explained you how in is calculated, out also is calculated the same way. So out is now pointing to this location. So again, if the consumer consumes another product, the out, okay, and the counter decreases. So in this way, if the consumer goes on every, then the counter and it will point to a position where it will point to no elements to be added. The counter, since the counter is 0, the consumer cannot consume any product until unless the producer does not produce a product. So how will this give an inconsistency of data? That is what we will see in the next slide, which is the race condition. So if we consider that the counter incrementing and counter decrementing in the consumer code, if they are executed using the registers, so the data is pushed to the register. So register 1 is used to add the counter for the producer, and register 1 is equal to register plus 1, because when the producer produces a new product, the counter is increasing. So the number of products in the buffer is increasing. So register has to be incremented. So counter is assigned that new value, that is there is register 1. Similarly, if you consider the consumer's code, we use register 2 to manipulate the data for consumer data. So register 2 we are assigning counter. Supposing now the counter value, both register 1 counter we have added 5. So in register 1 we have put counter value as 1, and in register 2 we have put the counter value as 5, as I explained in the previous example, that we added 5 to both. Now producer increments by 1 and consumer decreases by 1. So what will be the total counter value? Counter will get register 1, and here counter will get register 2's value. So 5 plus 1, counter will get here 6, and here counter will get the value 4, because 5 minus 1 will be 4. This is the inconsistent value, and this is called as a race condition. So if you see here, consider this execution interleaving. Interleaving means executing same time, simultaneously they are getting executed. Producer process also is getting executed, consumer process also is getting executed. They both are getting executed same time, maybe on two different processors on the same system, but they are getting executed simultaneously, and hence we have this problem. So if count value is initially 5, then this is all the sequence that it takes. If not, the first instruction that gets executed is producer executes register 1 is equal to counter. So 5 goes into register 1. So register 1's value is 5. Next, S1, second instruction. Producer executes register 1 and he increments the register 1. So register 1's value is 6. Next, third instruction is consumer executes register 2 and it decreases the register's value. Sorry, here it assigns register to the counter value, and next it reduces, and hence register 2 will get the value 4. Next, producer executes counter is equal to register, means whatever the manipulated value of the counter, that is saved back into the counter variable. Now counter will get the value 6, because producer is incrementing and consumer it is decrementing, so counter is equal to 4. So that's why the counter has got a wrong value. The actual value that counter should have right now is 5. So if we restrict this interleaving of this statement, means execution of this statement simultaneously, then what will happen? Only producer statements will get executed, or only consumer statements will get executed. So in that case, there will be no disturbance of the data, no data inconsistency will be avoided. So that is what we need to achieve. To do this, we need to use something called as a critical section problem. This problem, the part of that code, the producer code and the consumer code, where it is manipulating shared data. Who is the shared data now? counter is the shade data. Counter is used by producer also. Counter is used by the producer as well as the consumer. So we need to take care that this variable counter should not be manipulated by both. So that section of the code where the counter is getting manipulated in the producer code and in the consumer code is called as a critical section. It is the part of the code which is the critical section. Critical why? We call it critical because it can have a wrong value at ultimately. So consider a system of n processes, P0, so on, P1, so on till Pn minus 1. Then consider the system of processes. Each process has critical section segment or of code. So there is a part of the code that is manipulated by both the processes. So you need to take care of this section as a critical section. This section is called as a critical section. The process may be changing common variables, updating tables, writing to files, etc. Now what is this? Common variables, because now counter was a common variable which was being manipulated by both the processes. Next we have updating tables. Example is database tables. Supposing railway reservation is done online. When railway reservation is done online, multiple people are trying to access the particular seat and book the same seat. So that is an issue. So if there is a database table that somebody is trying to read and another process is trying to insert our data or update that data, then there will be data inconsistency. So we should take care of such situations. Next one is writing of files. Even files. Supposing if we are working on a collaboratively working on a file, means a group of people are working on a file. No two people should be allowed to manipulate the file simultaneously. So if there are n people reading the file simultaneously, that's not a problem. Let them read. But if there is somebody reading and somebody writing, if there is two people writing, then there is an issue. So we should take care that two people should not write the file simultaneously. These are some of the examples of a critical section. When one process is in critical section, the other processes should not be in their critical section. So we should take care of this. The critical section problem is design protocol to solve this. So we need to have a design to solve this problem that two processes should not be there in the same critical section. In their code, critical section, both processes or more than one processes that are cooperating, they will have certain part of the code where it is called as critical, means that is where it is accessing the shared data. Each process must ask permission to enter the critical section. So whenever process 1 wants to enter its critical section, then it should take permission of all the n processes that are present, cooperating and working. They should take a permission of all the other n-1 processes that it is entering its critical section. Should I enter? Are you in your critical section? If the other process is in critical section, then the first process has to wait for the other process to exit the critical section. So always a critical section will have three sections. One is the entry section, next is the critical section, then the exit section, then there will be a remainder. Remainder means it is a path where it is not having any common attributes. So any section, each process must ask permission to enter their critical section in the entry section. So permission has to be taken in the entry section. May follow critical section. So after the entry section, there will be a critical section, and with the critical, after the critical section, there will be an exit section, and then the remainder section. The rest of the code will be present. If you see this using a structure, critical section, general structure for a process P1, it will be like this. We'll be having a do while. It's not necessary that it always have a do while, but probably most of these processes are infinite processes which they will be working. So there is an entry section, then there is a critical section, then there is an exit section, and then the remainder section. So permission has to be sought by the process in entry section. Once it gets a permission to enter its critical section, when it is in this part between the entry section and exit section, no other processes processes will enter their critical section. And then when it exits, it makes a setting such that other processes are intimated that I am leaving my critical section. Anybody who is interested to enter the critical section can enter the critical section. So once it finishes the exit section, it goes into the remainder section and it has nothing to bother about other processes. It will execute independently of other processes. The process where we have some common information to be updated, it is called as a critical section. So let's understand this with an algorithm. Here we have a do while loop. In this do while loop, there is a while condition inside the loop, do while loop, while turn is equal to true. So what we are doing, if process P solution. So what are those? The first criteria that it should have is, it should satisfy is that it should have mutual exclusion. What do you mean by mutual exclusion? Mutual exclusion means in one class only one faculty can teach at a time. No two faculties can teach at a time. So mutual exclusion means if one process PI is executing in its critical section, then no other process can execute in their critical section. So that's what. If P1 is in its critical section, P2 has to wait in the it has to be in the waiting process till P1 exits from its critical section. When P1 exits its critical section, P2 can enter. So that is what is mutual exclusion. The critical section is always having only one process executing. No two processes can be in their critical section. The next one is progress. What do you mean by progress? Supposing if there are no processes that are executing in their critical section, neither P1 is executing nor P2 is executing. Both are not there in the critical section. Now both have showed interest. They both want to enter the critical section and execute the critical section. Who will enter first? That is what has to be decided by the processes. So, if no process is executing in the critical section and there exists some process that wish to enter their critical section, then the selection of the process will enter the critical section cannot be postponed indefinitely. Who will enter into the critical section cannot be postponed indefinitely. What will happen if you postpone indefinitely? If you postpone this decision indefinitely, all processes will go on block. So some process, at least one process, has to say that yes, this process, let it go for execution. So any one process has to be sent into the critical section. It has to execute and come out and allow the other processes to enter the critical section. If all postpone this decision indefinitely, then all processes will be on hang mode and none of the processes will get executed. So that is not what we want. We want the processes to execute fast and get good response time to the user. With less response time, the processes should execute. So we should see that the progress is achieved. That means that if any process wishes to enter the critical section, if there are n processes waiting, then any one has to be sent into the critical section and this decision has to be done promptly, not indefinitely postponed. Last criteria is bounded waiting. What is bounded waiting? Now if there are any processes that wish to enter into the critical section, then a bounded wait must exist on the number of times that the other processes are allowed to enter into its critical section before the permission for that process to enter the critical section. So if there are n processes, P1, P2, P3, P4, and there is a critical section in each of these, each process is having a critical section. So if P1 makes the resistors its interest to enter its critical section, P2 also is ready to enter its critical section, P3 also is ready to enter its critical section, then this processes who are waiting should not wait for other processes to repeatedly enter its critical section. Now P4 is entering its critical section again and again. These people have registered their interest. They are ready to enter the critical section and they are waiting. They are in the waiting state. And P4 entered the critical section, exited, again entered, exited, again entered. This should not happen. So any process, when it enters its critical section and it wants to again enter into the critical section, it should take care that there are waiting processes and those waiting processes should be given time for execution. So when they are waiting, this process should wait for them to finish because they are already in the waiting period. So if they are waiting, you should take care that these processes should not wait again and again for the other process to enter. So the number of times that other processes are allowed to enter their critical section after the process has made a request to enter its critical section and before that request is granted. You should take care that there is a bonded wait. So if this process is going to wait for indefinitely for other processes only to enter the critical section, what will happen to this process? This process will get blocked indefinitely. So you should take care that the processes do not get blocked indefinitely. So if this process has shown interest and it says that it is ready to enter the critical section, it should be allowed to enter the critical section in a wait time which is bonded. The wait time should be limited. It should not be unlimited wait. In this critical criteria definition, we have not considered we have not assumed that the processes, we have assumed that the processes are executing at non-zero speed. These processes are executing at non-zero speed, means they are live, they are executing, they are currently executing. And second one is no assumption concerning relative speed of the end processes. That means one process, what is its speed with relation to the other process there is no assumptions. We are not having any assumptions on that. And we have an assumption that all processes are active processes. They are executing. They are having non-zero speed of execution. Next, critical section handling in OS. Operating system. How does it do? Now we are talking till now we talked about general. Now let's understand operating system. In operating system also we have multiple threads and we have different processes that are cooperating, right? So in that case, how does the operating system critical section problem issue is solved? First of all, very less there is a situation of critical section problem. If they are, then we have to take care that we have to see whether the kernel is primitive or kernel is non-primitive. What will happen if the kernel is primitive or non-primitive? That means kernel is primitive or non-primitive means the kernel process, if it has got the CPU for executing its process, then it should be any other process that wants the CPU, can it remove the current running process and take over the CPU? Is primitive. And non-primitive is that if there is any process that is allocated to the CPU, then until unless that process doesn't finish its execution, another process cannot stop its execution and take over the CPU. So this is primitive and non-primitive. We have already understood this in our process chapter. So a primitive process, if it is a kernel is primitive, it allows preemption of process while running in kernel mode. And non-primitive process, if it is a non-primitive process, then there is no question of critical section problem. Why? Because if process P1 is given the CPU, it will finish its entire execution and it will leave the CPU. It will not make the CPU, it will not allow process P2 to block process P1 and take over the CPU. That's why if it is a non-primitive, it's the best option because run until exit kernel mode and blocks or voluntary yields the CPU. So it itself leaves the CPU or it blocks itself. So that is how the CPU is given to other processes. So in that case, the critical section problem will not arise. So this is this will not create a race condition. But primitive processes, if the kernel is primitive, then there can be a race condition. So when we have a primitive and non-primitive, you will say then best is to have non-primitive processes, operating system. Why? Because it will not disturb any process, any data inconsistency will not be available there. But if it is primitive, then obviously there will be a problem. But when should you have primitive and when should you have non-primitive kernels? Primitive kernels are very efficient, they are very needed when it is a real-time system. Because in real-time systems, whatever is the current requirement, the CPU has to execute that process on priority. That is why it is called real-time process. Whereas a non-real-time process, a normal process, then non-primitive kernel or operating system is good to execute. But if it is a primitive operating system is required when you have a real-time. The first solution solution is Peterson's solution. Peterson's solution is one such solution for solving a critical section problem. How you can make two processes cooperate and execute the shared data structures, manipulation of shared data structures. How you can manage that? There is a solution, that is a Peterson solution. Peterson's solution is a very old solution. It is not so useful on our modern computers, which is having multiprocessor system and a lot of the things. It is good for older ones. Another disadvantage of this Peterson solution that it works only for two processes. Only two processes can be involved in this solution. If there are n processes, then this will not be the best solution. Okay. Then what are the other things? It has two shared data. It assumes that load and store machine language instructions are atomic. So the load and store instruction. What is this load and store instruction now? Data that is loaded to the register is the load instruction, which uses the load instruction, and store instruction is when data is taken from the CPU registers and put back into the memory, is called as a store instruction. Like we had in our example, register 1 is equal to counter. This is done using load, and counter is equal to register 1. This is 2. So when you are getting a data from a variable and saving it into the register, we use the load instruction, and when we are getting the register value and saving it into a memory location in a variable, we use the store instruction. What do you mean by atomic now? Atomic instruction means these instructions, when it is getting executed by the CPU, these instructions cannot be preempted. It cannot be interrupted. In between only it cannot be stopped. It has to finish the task of loading or storing, and then only the CPU can take up the next job for execution. So that is what is the meaning of atomic. The two processes share two variables. Now we said that there are two processes involved. These two processes will share the variables called as int turn and boolean flag. This boolean flag, turn indicates whose turn it is to enter into the critical section, and boolean flag is used to indicate whether the process, that particular process, wants to go into the critical section. So the variable turn indicates whose turn it is to enter the critical section, and flag indicates that the flag array is used to indicate if the process is ready to enter the critical section. So if flag of 1 is equal to true, implies that process P1 is interested to enter into its critical section, is ready to enter into its critical section. If flag is equal to 2, flag 1 is equal to true, it means that second process is ready to enter into its critical section. So flag 0 and flag 1 is used for process P1 and process P2. So this is the algorithm for Peterson's solution. So what does this algorithm tell? Just go through this algorithm and try to understand what is being done here. We have seen flag of I is equal to true. This process, this code is for whom? Process PI. PI is process. This is code for process PI. Flag I is equal to true means what? That PI process is ready to enter into its critical section. Turn is equal to 2. What we are doing? This is process PI, and we are saying turn is equal to J. Means what? We always have that habit. You first, right? So that is what is done here. We are saying let J enter its critical section first if it is flag is true. So if flag of J is true and turn we set as J, that means if flag second process, the process Pj wants to enter into its critical section, let it finish first. I will go later. That is what is process P1 telling here. So process Pi says turn is equal to J. So and then we have the waiting process. While loop over here, while flag of J and turn is equal to J indicates that if it is the either flag, the flag and turn both are equals to true, then it means let process Pj enter its execution into its critical section and execute the critical section, and I will wait for process Pj to finish. When process Pj will finish, when it sets its flag as false, or when turn is equals to I. Either the turn value has to change or flag value has to change. If any one of the value changes, then this condition will become false and it will enter into its critical section. The PI will enter into its critical section. Then flag of I is equals to false. Since it finished its critical section, it will assign its flag as false. Why is it assigning its flag as false? To indicate for the process Pj that if you want to enter into your critical section, you enter into your critical section and execute the critical section. Then after it sets the flag false, it will enter into the remainder section and go back and execute. So what is happening? So flag initially it will be false. So when it wants to enter the critical section, the process will set its flag as true and it will wait. First it will give the chance to the other process to run its critical section, to enter its critical section. If the other process wants to enter into its critical section, then it will execute that, or else it will. So if the flag of the other process, if it is not ready for entering into its execution, into its critical section, flag value will be false. So anyone false indicates the while loop is false. So it will come and enter the critical section. So this is how a Peterson solution is designed. Does Peterson solution prove all three critical section requirements? Does it meet all the three critical section requirements? What are the three critical section requirements? First one was the mutual exclusion. Second one is progress. Third one is bounded waiting. So are we achieving all three? So mutual exclusion is preserved. How is it preserved? P1 enters the critical section only if either the flag of J is equal to false or turn is equal to I. So any one condition, then only it enters into the critical section. Second one is progress. How is it achieving progress? What was progress? Progress was that if there are n processes waiting for the enter the critical section, then this decision of who is going to enter next should not be postponed unlimitedly. So that is achieved here. How we are achieving that here? Just mutual exclusion we are achieving with this while loop. So if any of those conditions, both the conditions are true, then it has to wait. If any of the condition is false, then only it enters the critical section. Okay. Now how we are achieving progress? See here we are saying that flag of I is equals to false, and there we are saying turn is equal to J. So when we are setting turn is equal to J, we are, before Pi enters into its critical section, it is telling that process Pj can enter critical section. And then how we are achieving bonded wait? We are achieving bonded wait because we are, as soon as we finish the critical section, we are saying flag of I is equal to false. This flag of I false indicates that Pj can enter its execution because it is already waiting, then it can enter its critical section. So this is how we are achieving all the three criteria. Next is synchronization hardware. So through hardware also we can provide process synchronization. So many systems provide hardware support by implementing the critical section code. All solutions below mentioned on the idea of locking. So we use something called as a locking system. This is basically the hardware system. So any process who wishes to enter its critical section will have to acquire a lock. When it finishes executing its critical section, it will have to release the lock. So we will see each of these. Then uniprocessors could disable interrupt. If there is a single processor on a system, it will disable interrupt. So what will happen? The running process will finish its execution and then only the next process will be taken for execution. So in this way also we can achieve that the critical section gets executed undisturbed. Next, currently running code would execute without preemption. That is what is disabling of interrupters. Then we also have two other options. Okay, multiprocessor, in a uniprocessor system you can disable interrupts. That's not a problem. But in a multiprocessor system you cannot disable interrupts. That will be a problem. What is that problem? Because in multiprocessor system, if you disable interrupts, if there is a CPU running, if there is a system with supposing four processors running, four processors in it, then there will be four different processes will be executing on those four processors. So CPU 1 will be executing process 1. So if I have CPU 1, CPU 2, CPU 3 and CPU 4. So process may be process may be executing here. So in this case, if any of these processors become free and if new processor comes, new program comes for execution, then it will be difficult if we disable interrupts. Then another thing is interrupts also cause little time wasting if we are having four processors, and if we said that we disable interrupts, supposing if I disable interrupts on this, then it will actually not achieve the efficiency that we can with four processes, because some of the process may not have time or the response time of the system will reduce. So it is not a good idea to have disabling of interrupts on a multiprocessor system. But if we have interrupts and if there is a process that is waiting to enter its critical section, any interrupt that comes in, any interrupt that enters the system, the interrupt is sent to all four CPUs. The interrupt signal is sent to, or message is sent to all four CPUs. So what happens is, the process to enter into its critical section, then the time that is required to enter the critical section increases, because CPUs are trying to read the message, understand that, and take a decision of who is going to execute this interrupt. So that's why there will be some time delay in execution, and this will reduce the efficiency of the system. So it is operating systems with multiprocessor systems not disable interrupts, because it will affect the scalability of the system. So modern machines provide special atomic hardware instructions. Atomic in the sense non-interruptible. So instructions are all atomic. So the execution is without any interruption. And hence we have solutions like test memory word and set value and swap contents of two memory words. These are the two solutions to execute process synchronization on a multiprocessor system. So we have talked about using locks. So this is an example wherein we are trying to execute critical section problem using locks. So we have a do while loop, and in that we say acquire the lock. The lock is a hardware lock, remember this. So whenever a process wants to enter into its critical section, it has to acquire the lock and then enter the critical section, execute the critical section, and then release the lock. So that is what is here. So acquire lock, execute the critical section, release the lock, then the remainder section. So a lock is a single lock. So if one process gets the lock, then the other processes have to wait for that lock. So until unless this process does not finish its critical section execution, it will not release the lock. Since it will not release the lock, other processes have to wait for the lock. So that is how we are achieving process synchronization with hardware. That is one way. Then the other way is test and set instructions. So we will see this in the next class. Thank you.